Okay, this is a short introduction to Biomorpher component using one of the examples included in the latest release, 0.2. This example is called boxes, and it's very simple. It's just a series of boxes, domain boxes, set by these parameters set up by gene pools. And we find the bounding box from those boxes, and then we literally just subtract those boxes from the bounding box. And there's 10 boxes in all. Within those 10 boxes, obviously, we have a domain, X, Y, and Z domain. And combinatorially speaking, this is pretty vast. Even this very simple problem, I'm just going to show you some variants of the gene pool. Let's just change some of these parameters. It might look a little bit different. Okay, they're looking slightly more hollow in the center. And obviously these shapes, if I just look at these boxes here, you'll see what's actually being subtracted away from this bounding box that's slightly scaled. It's very simple. It's kind of proof of concept example, but it does introduce some of the basic concepts quite well of Biomorpher and the capabilities that we think it has. One thing to say, we've also got this parameter here, which is colors. The latest release allows mesh colors. Unfortunately, like WPF doesn't do any vertex shading or anything like that. So I'm just trying to work out the best way in the next release to get this much better. At the moment, it'll just take one color from the mesh. Maybe if we put in a list of geometry in future, we can color that. Ideally, I'd like to look at vertex coloring, but as I say, it's kind of transitioning to WPF format in Windows is not great. So we'll see about that in the future. This subtraction with this geometry is done here, and then we have a result where the volume is taken, and if we have a couple of components, I'm just doing a mass addition, so the end volume is a kind of total thing. So this is 162 meters cubed, whatever that means in this context, and here we have mesh geometry. We pop the mesh geometry into the component itself. So if any of you have used Speckle, it's very similar in that sense that we have to input the geometry and the performance data, and we input the parameters. And we don't have to flatten this, it does flatten them automatically, so if we have any trees going in here, it's not going to get angry or anything like that. Essentially, every time I change one of these designs, obviously the volume changes, and that's the performance for that particular design. And these are the inputs then. Biomorpher will take genomes, much like Galapagos, it will take gene pools and it will take sliders. You can actually, if I were to take one of these away, I could select it again, and you can right click on the component, and again, a bit like Galapagos, you can just say add this selected slider or take them all away, etc., etc. And we have this here. So if I double click on this one, I end up with the main window for Biomorpher. So I can click exit any time, but I'm just going to double click and it opens a new instance of this window. Now there are some initial settings for the population. In this case, we're going to have a population of 100 different designs. That is 100 different parameter states, essentially, for our model. And we're going to set this mutation probability. I'm just going to set it at 0.02, which is essentially 2%. In Galapagos, it's the same. Genes can cross over and they can mutate. Here we don't do crossover, we just do the mutation. But mutation is gene mutation, so it's the chance of a single gene or a single parameter or a single one parameter in the gene pool mutating slightly. And the amount it mutates is just based on a random number. So we could have that as another variable, but one of the philosophies here is to try and keep things reasonably clean. And so we have this design, we have the population tab. If we hit the About tab, you can see a bit of information on the latest release, where to find the grasshopper groups, some of the dependencies that we're using in the license. The license is MIT, which pretty much means you can do what you want with the software. And we're not responsible if it crashes Rhino and you lose all your work, that kind of thing. It is quite an early development at the moment, so it can crash Rhino sometimes with incredibly complex models. So just be wary of that and make sure to always save your work. These are really early releases, so that might happen. Okay, so we've got 100 designs, and I'm going to hit go, and you can see when I hit go it will start searching through different combinations of parameters based on the ones here. I mean, here you see I've got 63 values. So 63 parameter space, so essentially a 63 dimensional parameter space. And you can see in terms of combinatorial problems as they go, this is like obviously, even a very simple model like this, combinatorially is completely vast. And that's why these tools, I think, might help kind of search that space. Right? Anyway, we've hit the go button. We've got this population of 100. We can't change that now. That's kind of our first generation of designs. And you get these kind of weird spider-like things appear. So you might think, okay, what's going on here? What's going on here is every point represents a design. So essentially it represents a set of parameter states of those 63 parameters. And one thing about interactive algorithms, something like Galapagos, you might have a population of 100 and it might measure against an objective function, like you're trying to minimize deflection or you're trying to maximize the amount of shade or something like this, or the shadow casting. With Biomorpher we can have those performance values, and we've added this volume performance value for instance, but we're also trying to view designs and be able to pick them for the next generation according to kind of more qualitative measures. So, you know, something that feels right for the next generation, or there might be something that can't be defined by numbers, you know. And that's kind of the idea behind this tool, is to try and integrate those into the search. But if we have a population of 100 designs, we can't display 100 designs. It's very hard for us humans to cognize 100 designs associatively. So we want to reduce that to say something manageable like 12 designs in this case. So we have we use this algorithm called Kmeans. Kmeans is just a very simple clustering algorithm that will take a group of designs and it will say, okay, if I've got 100 designs, what 12 designs best represent the space, the parameter space of my kind of parametric definition. So for instance, this design here, this 0 design actually represents 3 designs, and the one in the center is the one that best represents these 3 designs. In this case, we have a group of designs that are very closely related compared to this group, and therefore we have much more. So we've got about 20 or 25 different designs here that are represented by this one design here. So that means to say that this design here in the center is very similar to these designs here. Now, when I say similar, it's similar in 63 dimensional space. So it might be color, it might be the X domain, variable, all these things. And those that know anything about this kind of thing will know that this relies on a direct mapping between parameter, like genotype, if you like, and the phenotype, the solution space. There's not much we can do about that at the moment, because if we were to calculate the solution space of 100 or even 1,000 different designs, obviously it would take Grasshopper a bit of time. So we kind of play off and we kind of say, well, you know, because these are DAGs, these are kind of directed acyclic graphs, that we might get a reasonably direct mapping between parameter and solution space. That is a bit of an assumption, and in future versions we'd like to kind of look at the difference between parameter space and solution space. But at the moment we're just looking at parameter space in this thing. So parameter space, basically, I mean, you know, for this one design here where my mouse cursor is pointing at, or even the one at the center, there are 63 parameters that are represented by that. That's the parameter space. Now, what those parameters do, they generate some sort of geometry, and that is our solution space. This is our kind of phenotype that's generated through our graph. And in the new version, we've got this comparison between cameras. So we'll track the camera. It makes comparison between designs a bit easier associatively across these different designs. So what you'll see here is if I double click on a design, you can also display this design in Grasshopper itself. This can become useful obviously if you've got more context that you haven't added into Biomorpher and you want to kind of go into more detail about what the design actually look and feels like. Maybe you've got something that you're using with human and some materials, I don't know, whatever. And that's how you view that. You can just double click on these designs and they display them. So, and it even says this here, right? And every time I double click on the design, you'll see the properties of this design pop up. And the properties are essentially the performance values that I put into the component here. So you can have quantitative metrics that are judged with each design, but it's how you combine that with the kind of qualitative, non-defined, the things that can't be defined numerically, and that's what this tool's all about. But anyway, so if I look at this one, 402, and you'll see it matches the same here, and it also picks up the parameter name. So this, because it's R, I mean, I could actually right-click and change this here, and then this would display differently. But you don't need to enter anything here. It's like all picked up automatically. And I just pan around these designs. And I can pan and orbit and all these kind of things. This is the Helix toolkit. It's actually similar to what's used in Octopus. Okay, so the other thing to say are these colors up here. Now, although we're saying that you can pick these in a qualitative sense for the next generation, we also have this little kind of color code that shows if we have a parameter like this one, r equals 4/2, and I just double click this, we hear r is 452, the volume in this case, and down this one has the lowest volume because it has the lighter color for this performance value, and the minimum and max are highlighted with this circle around the outside. So I can double click on this one, I can tell it's like 194, and this one is 452. So these kind of are the min and max values for this set. And if you have more performance values, they'll appear here in different colors, and just have a look at some of the other examples. So I'm going to pick a couple from my next generation. You do that by just selecting the checkbox, and it doesn't just pick these three, it picks all the ones in the kind of population that are being represented by this cluster. So I'm just going to go for these bluey purpley ones. My initial idea is to try and eradicate these colors here for reasons I don't know why, but I kind of like those blue and magenta-y ones, and I'm just going to click evolve. So we should see in the next generation a little bit more. So we have some variation, some red ones and green ones, but we're kind of getting a little bit more like the bluey and purple ones. Again, this is the next population, and I can double click and have a look at these in more detail. I can also go back and I can change the mutation rate. So if I wanted to up the mutation rate really high, obviously if I went to the next generation and I just evolved these designs, to the next generation, you see it just gives me a completely new spread because the mutation rate has just done something completely random. Okay, so let's kind of turn this down to something more reasonable, like 0.1. And if I select one design for the next generation, I'm just going to pick the most voluminous one and click evolve. You'll see we end up with some designs that look kind of similar to this one. They're not all the same, and we end up with some that are like really, really hollow. But we get these kind of, I mean, this one's actually quite interesting. I think I might select some of these green ones for the next generation. And you can see this whirling in the background, right? It's looking at these different variations. And again, I can just double click on these. Have a look around. I'm going to select, I quite like this one that has this kind of hollowed out center. I just clicked evolve and it's going to give me a new set of these. So you know I'm getting this kind of C-shaped design. And let's just go for these navy ones now. And it works on the basis of elitism, so if I select a design, it's more likely it's going to be included in the next population, but it's no guarantee. And it does a kind of roulette wheel search for the next generation, a roulette wheel selection, sorry. and we have these designs. Now in the latest version we also have this history tab where we can look back at earlier populations. So let's go back to this green population. I'm just going to click reinstate, and of course, I mean, this is quite a simple, you'll remember this one from before, but this is obviously a simple geometry. It's more of a proof of concept than anything else, but you'll get the idea that something that's more relevant, a parametric model that's more relevant to your problem, might actually be more useful. But I'm just going to go to this one now. I'm going to select this pinky purpley one, and we're going down. So essentially we're going down a different evolutionary route. You see these little mutations between these two, and what happens with the Biomorpher history is that we see where the new population has kind of sprung from, and we start a new generation here. So I can now kind of go select these designs, evolve them. Okay, and then I'm just going to pick these. It's hard to say how I would like some of these designs, to be honest. But, oh, this is quite fun with these kind of grooves in it. It's almost looking like a house here with the chimney. Or a face. And I go back. You see my clusters have started to kind of bunch up slightly. I can kind of release that by increasing the mutation rate if I feel like, but I'm just going to keep those like that. And I kind of like these. You've got a little doorway like coming up here, and this is like a little castle. And again, let's just double click on this, and I can have a look at this in more detail in Rhino. And if I go back to my history, you'll see, now, I mean, in future generations, we want to include things like performance data, and double click on these and have a look at these in more detail. We can't have these as all orbit windows because it just takes up way too much memory, essentially. So we have these little preview windows. They're not actually images, they're actually these themselves. The benefit of them not being images is that we can export this, a PNG file. So I'm just going to pop this onto C, and I'm going to say tester. Oh, I don't have permission. Okay, let's put it in this university machine. Let's just put it in my documents and go to tester, PNG. And then if I go back to here, you see I'm running a very recent version of Windows here. And I go to tester, you see it exports this image of the PNG itself. And the resolution is okay. I mean, it's 300 dpi. It's kind of funny, these have gone a little bit wrong. I'm not quite sure what that is. I have no idea, to be honest, but it shouldn't do that again. You can try and do that again, and let's see if it does it again, actually. Let's go to tester. Let's just replace it. Okay. It does it again. Okay, so there's something we might need to look into. Probably make a note of that. I wonder why it's doing that. Obviously some weird graphics thing. So I close the window now, the Biomorpher window, and I'm left with this design where I was. In future versions we'd like to save that. You'll be able to save the history. It's the first version of the history that we've done, so there's a lot to kind of be added, and you can reinstate old populations. I think I might leave it there. I've talked quite a lot. I would advise though, just have a look at the examples. Let's just have a quick look at one of the other examples. So this one, which is to do with, so these are kind of little kangaroo sculptures. Shameless use of kangaroo 1, I'm afraid, and not 2, but here we're just looking again, I think this is a volume 1, but we're combining zombie kangaroo with looking at different forms that look a bit like the artist Henry Moore sculptures. And so these are the phenotype outputs, and I can just evolve these, and you get an impression for slightly different ways this can be used. And finally, you might say, okay, why don't we just have populations of 12 instead of 100. The reason for that is that in future we'd like to incorporate target-based optimization in the same run as a kind of more qualitative based optimization. So there's lots of benefits with large populations in things like genetic algorithms where we're looking at targets. So we might say, minimize deflection, that kind of thing. But it doesn't work with interactive algorithms. So using this Kmeans approach, we want to kind of combine the two and try and have those two exist in the same evolutionary run. Anyway, thanks for listening this far. Hopefully that gives you an idea into some of the benefits that this tool can provide. Early days, so please leave your feedback and any projects you manage to or maybe trial this out on. Just pop it on the group. I would be really grateful. Cecilia and I will be very grateful, so we know where to push things going forward. Okay, thank you very much. Bye.